Right, so I will share my screen. That one. Okay. Welcome everyone again. And we're going to jump in straight away. I'm a couple of minutes late. We had some interesting discussions on the other Zoom. That's why. So sorry about that. Okay, today we're going to talk about objectives, and that's lots to be said. So we've seen this already once, a very nice video by Jeff Lichtman about the point spread function and the way it forms with these little wavelets that form at the basically the front lens of the objective, and then more and more wavelets. We get this very interesting and artistic refraction diffraction and interference pattern. And then when we have more and more wavelet, we end up having like one big blob, elongated blob in the center. And that is the image that each floor forms. It's the point spread function. So we have seen already that. Point spread function is a little bit like the brush for a painter. If you have a very, very big brush, you cannot paint a very fine painting. You have to have a small brush for that. So if we want to paint a very nice detailed painting of our sample, we have to have a small point spread function. So we try to do our best to reduce it as much as possible. But we can't reduce it forever because we're limited by the physics as well. But we try to not to make it bigger than it should be. Oh, here we go. So let's see how we choose an objective. There are lots of different aspects of an objective. It's not just about the magnification. A lot of people speak about I chose the 60x or I chose the 20x. So we have a tendency to think magnification, and that's really not the main part of the objective. But the objective is one of the most important parts of the macroscope. So don't use an objective just because you don't know why. You pick the best for your experiment and you design your experiment, right? So people will tell you, oh, just use that one, but just think. The objectives are extremely expensive. Well, it depends which ones, but the good ones can be really up to 220,000 euros. So take care of them. They are really costly. It takes sometimes several months to get them fixed if there is a problem with the front lens. You can see in here these two point spread function, and this one is clearly distorted compared to that one. These are real measurements. So actually the difference between these two is the change of refractive index of the oil put on the objective. So you can see the dramatic effect that this has on the point spread function. And we do quality control of our objectives with sub-resolution beads. And when we see something like this, where the point spread function looks a bit like a banana, or it's very asymmetric, it's always a little bit asymmetric, but very asymmetric and much longer than it should be, or much wider, then we think that the objective might be damaged, it might be dirty, or there might be the wrong immersion medium on it, which is the way it is right now. So the point spread function is a great way to actually quality control the objective. I think many core facilities do that. So let's go through the different specifications of objectives so that we see what we have to consider when we choose an objective. One of them clearly is the field of view and the magnification. So that's the one we think about straight. And that is always written on the objective. It's a number followed by an X. And this is true for all manufacturers. It's always like this. So this determines the field of view. And that means, what is the field of view? It's the size of the sample area that fits in the image. So that depends on the magnification, but it depends also on the size of the other things, like, for example, the sensor and the microscope. But clearly, if you have a lower magnification, you're going to see a bigger area of your sample, so you'll have a bigger field of view. However, if one has to choose an objective with a smaller field of view because of other specifications that we'll talk about afterwards, it is possible to compensate by acquiring many images next to each other and pasting them together. And this is called, different manufacturers call it differently. It can be called a mosaic, tiling, a large image, or an overview. All this is the same thing. We take many images next to each other and we assemble them in a big image. Show you. But that is a way to compensate for a small field of view. In some cases, we can increase the magnification without changing the objective, and we will talk about this throughout the course. We can add an extra magnification lens in some cases when we use a camera-based system, so that can be a way to increase the magnification without changing the objective. Another specification of the objective that is important, and it's sometimes completely limiting, is the working distance. The working distance is the distance between the front lens of the objective and the closest surface, which can be the one surface of the cover slip, or it can be the sample if we have an objective that doesn't work with cover slips. I will talk about that a bit later. So this distance here is limiting. So this is when the sample is in focus. So if we focus on the sample that is here, for example, what is this distance? This is the working distance. Why does that matter? Because if it's too short, when you want to focus here, for example, you're going to move the objective closer to the cover slip, and at some point you're going to bump into the cover slip, simply. So if you have an objective with a short working distance, you're not going to be able to focus deep into the sample. You will bump into the cover slip and you will not be able to focus. So before you reach the focus. So if this happens sometimes to you, that one day you come to your microscope and then you try to focus on your sample. Your sample is set up in the normal way. It's a slide maybe with a cover slip, and you try to focus on it and it's like, I can't focus. I just keep trying and it doesn't work. And then suddenly your sample starts moving like this in XY. If your sample starts moving from right to left, you know that you're moving it. So you're pushing on the sample. If you push on the sample clearly and you're still not in focus, there's a problem. The typical thing is that you forgot, for example, if you have an inverted system, you forgot to flip your sample and you're trying to image through the glass slide, which is thick, instead of imaging through the cover slip. If you have an objective with a short working distance, this is not going to be possible and you're going to bump into the sample. For that reason, I really recommend never to clamp your sample. Don't clamp it, except if you have a reason to clamp it. Do not clamp it, because if you end up pushing on the objective, I'm talking now about inverted system where the objectives are below. If you push and the sample is blocked, you may, break the sample, but you will also damage the objective. So don't clamp your sample when you have an inverted system. And when you're upright, be very careful, because then you can just crash. So this is an example of a Nikon 60X 1.4 oil objective. It has a working distance of 130 microns. And this working distance excludes, let's say, the cover slip. So the thickness of the cover slip is calculated. So this is really how much you can focus inside the sample. Okay. So that gives you an idea. If you have a sample that is thicker than this, you can't use that objective, simply. Something else that we have to think about when we consider the objective is the numerical aperture. So we spoke before about apertures. So the numerical aperture is a very important specification of the objective, and it's always after the magnification and the slash. So it's always magnification slash a number without unit, because this is a ratio. And then you may have other stuff behind. But this number is always the numerical aperture. And again, this is the same for all manufacturers. What is the numerical aperture? It is the ratio of, it's the multiplication of the refractive index of the medium that we put on the objective. So this is the immersion medium, okay, for example, oil, water, or maybe it's an air objective. So we have the refractive index of this multiplied by the sine of this angle. So this is the acceptance angle, the light acceptance angle. And you can see here, if you have this objective, we have a very wide angle. So if we have a fluorophore here that fluoresces in all directions, a higher proportion of the light emitted by the fluorophore will enter the objective compared to here where we have a narrow angle. Okay, so this numerical aperture is here, and it depends clearly on the refractive index of the medium that we use on the objective. Air objectives, if we calculate and everything, can never have a numerical aperture of 1. So 0.95 for an air objective is very high. For a water objective, anything above 1.2 is very high, and for an oil objective, anything above 1.4 is very high. So you will see all these. So this one is not a very high aperture because it's below 1.4, and it's an oil objective. So unfortunately, we spoke about the working distance before. The working distance and the numerical aperture, they play against each other. So when we have a wide angle, we have a high numerical aperture and we have a short distance. So it's a trade-off. So it's often like this in biology, it's a trade-off. But you remember that the aperture is an iris that is placed in the light path at a place where we do not have an image formed. And this limits very much, this affects the whole image, and it limits the resolution. So the numerical aperture is one of the most important specifications of the objective. It limits the XY optical resolution. It also limits the depth of field, so the Z optical resolution and the brightness. So then we move on to the next specification, which is the XY optical resolution. And there we have, so the resolution is the smallest resolvable distance between two dots, and it's often in nanometers in our field of microscopy. So it means that when we have a short distance, we have a high resolution, okay? We can put two dots next to each other, very close to each other, and we can still say it's two dots, we're happy. It's a high resolution, and it's a small distance. So in this course, we are going to follow two equations to calculate the resolution, the XY resolution. So it's going to be, the same equation for XY, and there will be one equation for Z. And I have chosen with good reason, so I'm going to argue my case that we're going to use the same thing for wide field and for confocal, or for non-confocal system and for confocals, whichever they are. We're going to use the same thing. And this is 0.61 multiplied by the wavelength of the emission and divided by the numerical aperture. So as you can see, the numerical aperture has a strong influence here on the XY optical resolution. In the case of a confocal, we have a pinhole, and when we can close the pinhole, then the contrast increases. But we're going to use this equation for the XY optical resolution for everything. Then the pinhole size and the XY optical resolution are not related, except if the pinhole is small. Okay, so you can see here that there is nothing in this equation that tells us about the size of the pinhole. So all this we will understand throughout the course, but basically, anyway, even if we use the very precise equations for confocal, the size of the pinhole is not included except when the pinhole is very small, like around 0.2 area unit, something like this. So when we close the pinhole, what happens on the confocal is that we increase the contrast. So let's have a look, and you can see, you can always find these equations. You will know them by heart because there's only two, and you will use them again and again and again. But if you forget, you have the important equations for light microscopy in the practical information module. Everything is there, and it's also sort of summarized. Yeah. So now the Z optical resolution, it's also called the depth of field. So what is the depth of field? It's characteristic that is very well known in photography. When you have a photograph like this, and you can see these are little mosses in the Swedish archipelago, and you can see in here the distance between this guy here, which is very well in focus, and this guy here that is very well in focus. So these two are in focus, and what is the distance? But they are not. This one is further away, so they are not in the same focal plane, if you want to say, but they are both in focus in the image. So this distance is the depth of field. So what is the distance between the thickness of the sample that appears in focus in a single Z plane? That is the depth of field. And this is actually what limits the Z resolution on the macroscope, the depth of field. So the Z optical resolution is the smallest resolvable distance between two dots located at two Z planes. But if two dots are at different Z planes, but it focus at the same time, we cannot resolve them, we cannot separate them, we cannot tell that they are at two different Z planes. So the depth of field limits the optical resolution, and the depth of field equation is the one that we're going to use to calculate the Z optical resolution. This is the equation, and we're going to use the same thing for both wide field and confocal in this course. So 2 multiplied by the wavelength of emission again, and multiplied by now the refractive index of the immersion medium that we put on the objective. So you see again, the objective has a very strong influence in here, and divided by the numerical aperture squared. So that means that in Z, the numerical aperture has a much stronger effect than in XY. It has an effect in XY, but very strong in Z. So changing to a higher numerical aperture objective will have a very strong effect on Z, more than in XY. In wide field, then we know we have a lower contrast for thick samples, and in confocal, the equation is again completely different if your pinhole is smaller than 1 area unit. So here we have the depth of field of 2 objectives, one with a high numerical aperture, one with a low numerical aperture, and here is the object plane, and you can see that the objects that are here are very, very much in focus, and then how much the focus goes down throughout the depth of field, we can have an object here and an object here and an object here, and they're not exactly in the same Z level, but they are all in focus, and we cannot then differentiate their Z level. So this is why the depth of field limits the resolution in our ability to separate objects in Z. So high numerical aperture objectives have a shallow depth of field, and only a thin section of the sample is in focus, and the rest is blurry. So it will be harder for you to find the exact plane of focus with a high numerical aperture objective. You need to be really careful to focus. And therefore, we need to have a focus strategy. So we will talk about the focus strategy also a little bit later. Again, this equation for Z is in the important equation for light microscopy. So I want to say that there are a lot of, let me hide this. There are a lot of things online. This is the reason why I put this equation for light microscopy, important equation for light microscopy document. Because if you say, oh, what was that equation again? And you Google it, you're going to find zillions of things. There's a lot of confusing things. There's lots of wrong things, clearly, but there's also correct things without the context. So just take with a pinch of salt, and if you forget the equation, it's better if you go back to the important equation document than if you try and find it online. It's a bit of a mess there. So we have the full width half maximum is considered also as resolution. The Rayleigh resolution, which is the one we use, is actually empirical. We have the Abbe resolution, is theoretical. And we have the resolution for confocal with infinitely small pinholes. It's not always written that you are in this case, and maybe it doesn't apply to you. And then the optical section thickness, the depth of field, the depth of focus I have found as well online for the optical resolution. And this is completely wrong because it refers to the camera. And then the Z step is sometimes considered, which is absolutely not the resolution, etc. Sometimes it's calculated for the excitation and the emission, sometimes the average. And sometimes there's an approximation. So believe me, don't go online to look at it. If you miss the equation, go to this document and then we will talk the same language throughout the course. After the course, you can pick the equation you want. So in reality, also the refraction and the scattering in the sample is often what limits the resolution. So please prepare non-refractive samples, and we will talk about sample preparation on Tuesday. So go back to this document when you need. There's another equation. That one is very, very simple. This is the brightness. And then you can see the impact of the numerical aperture. And this is like power to the 4. So that has a very strong impact. But we also have, and this is one of the few equations where we have an influence of the magnification. So the magnification influences the brightness. Everybody wants to go higher in magnification, right? But look at that. The magnification is at the bottom of this equation. So if we compare, for example, two objectives, one of them is a 40x oil Na 1.3 and a 60x oil Na 1.4. So the numerical apertures are quite close to each other. The magnification is quite different, okay? And both are oil objectives. And when we calculate the brightness with this equation, and I tend to multiply by 1000 because otherwise you get lots of digits behind the comma. This is what we get. The 40x oil Na 1.3 is actually much brighter than the 60x oil. So it is not the case at all that you want the higher magnification, the better. Sometimes we have people who tell us, I want 100x. I can't see what I want 100x. And the 100x's, most of them have the same numerical aperture as the 60x. So there are some circumstances where we would use 100x, but not many. For most people, the 60x is actually a much better choice if they want to have the best absolute resolution. And you can see that in many cases, you would be happy to give up a little bit of resolution, because you can see in here, this is the XY resolution, and this is the Z resolution of these two objectives. And you would be happy to give up a little bit of X, Y, and Z resolution to get such a bright objective. So the immersion medium is very important. You have seen this little n that comes in several of the equations for the objectives. And so the immersion medium can be different things. It could be an air objective. It could be a water objective. So in that case, you put water on the objective. It could be glycerol or silicone and oil. And I've ordered them here in the order of refractive index. So here are the refractive indices of these. And you can have also an uncleared sample. It can be anything from, if it's like cells on a cover slip, that is quite close to water, so we'd say it's about 1.3. If it's a tissue, it's often around 1.4 something, and it's a very fatty tissue, it can reach up closer to 1.5. So anything pretty much with uncleared tissues, and the embedding media match anything between water and oil. And then we have glass, like for example, when we use a cover slip, it's 1.52, and this is the same refractive index as oil. And then we have also some things at the bottom of a dish that can be optical plastic. And these optical plastics, they usually don't go all the way up to 1.5. Things change a lot, so I don't know if there are new materials that go all the way to 1.5, but mostly they are for lower refractive indices. Fortunately, our samples are often heterogeneous, and very often they have a different refractive index for the one that we the one that we put on the objective, the medium that we put on the objective. So there we have a problem, which is refractive index matching, and we will talk about this today. And this is exactly what we have here. I've shown you this before, where we have refraction and lots of things happen there. The light is changed, the wavefront is, the speed is changed, and the direction, and so this sort of things happen. So also happens when we image our samples. The next thing that we need to think about when we choose an objective is the sensitivity to aberrations and if there is a correction color. So some of you, I've asked you to list all your objectives before, and one of the questions I think was, is there a correction color? And this is what I mean. So in this, or on this objective, there is a ring that you can actually turn. And there is a gradation here or some markings in here. It's always like this. So not all objectives have this type of rings. The higher the numerical aperture and the more sensitive the objective is to aberrations. And very often, this is the reason why there is a ring. Objectives with a ring are very sensitive to aberrations, and therefore the manufacturers add the ring for you to actually adjust to the conditions, the imaging conditions that you have. And that means that the objectives that have a high numerical aperture, so this is, I remind you, this is an air objective. So 0.95 is very high for an air objective. So this objective is considered having a high numerical aperture, even though it's only 0.95. This objective will be very sensitive to anything that goes wrong in your sample, and therefore there is a ring for it. And that means that if you have a ring, you have to use it. So the aberrations can be corrected manually if there is a ring. And sometimes the ring can correct different things. So it could be, for example, temperature variations can be corrected. If an objective is sometimes at room temperature and sometimes at 37, you can have a ring like this. You can have the cover slip variation thickness. So please always use number 1.5, but some objectives, actually like this one, have a ring that can allow you to have a little bit thicker or a little bit thinner, but it should be set to the correct place, okay? The easiest is to leave this in the center and only use 1.5. And then it can be also, some objectives can use different immersion media. So then you can set this ring to be for water or for glycerol, and then you put different immersion media on the objective. When you use a high numerical aperture objective, always check if there is a correction color like this one. If there is one, always adjust it. This is important. And you put a lot of effort into making your sample, and it takes sometimes years to prepare a sample if you want to count the mouse that you have grown and everything. And then at the end, you don't change the ring. It doesn't make sense, right? So use the correct cover slip, number 1.5. The sample should be directly on the cover slip, not on the slide. We will talk about this again. And you should match the refractive indices of the objective immersion medium and the sample. This is what happens if you don't. So basically, these are two images of sub-resolution beads that are acquired with a high numerical aperture objective, 100x oil and a 1.49, which has a ring. And what happens if we take these two images with the ring set at different positions? And I assure that you that in both cases, this was the best focus I could get, okay? So you can see that the image is much dimmer, it's much grainier, so there's a lot more noise in this image, and it's much harder so the image looks out of focus, like quite strongly out of focus, but this is actually the best focus we can get. You will only see the difference between a ring that is set the correct way and one that is not, if you look at the images side by side. If one day you go to your objective, it's like this, you're not going to go, oh, it's a bit bizarre today, but you're not going to realize that all you have to do is turn the little ring and then it will be much better. So if your objective has a correction color, use it, and the images will get sharper and brighter. And then if you do not adjust the ring, it's exactly the same thing as when you do not use a correct cover slip. Okay, so so you will only notice the difference if you look at the images side by side. So one needs to keep a critical mind. If you notice that something is blurry and is normally not blurry, something is wrong. So another thing that we have to think about is the cover slip thickness, which is part of the design of the microscope. So the cover slip, the immersion medium, so that's the one we put on the objective, is called the immersion medium. And the mounting medium, this is the one you put on your sample, are part of the design of the objective. So the manufacturers have to assume some things about your experiment when they design the objectives, and they assume a number of things. And yes, I heard someone say, and I really liked it, that the cover slip is the cheapest optical element on the microscope and the most likely to be misused. Just ban anything else than 1.5 and you will never hear me say anything about your cover slips again. So some objectives are designed to work without cover slip. So that's also important to think about it. If you put a cover slip on your sample, the image is going to be distorted with these objectives. So you can look at the objective and you will see on the objectives very often, you will see which cover slip thickness is recommended. This corresponds to 117 microns. And it is called, by all manufacturers of cover slip, it's called number 1.5. So choose the correct cover slip thickness, and you can see in here it's written that we can go from like a thinner one to a thicker one as well. The center is 170 micron. And you can get a better one, 1.5H, and that means that the range is a bit smaller. They're also a little bit more expensive, but they're even better. This is an objective that is designed to have no cover slip. So it's called a dipping objective, and so you put it directly into the medium, and it's used on upright microscopes. So when the objective is designed to have no cover slip, do not use a sample with cover slip. Okay. So the live samples, for example, that are imaged from the top, and when they need a very long working distance and a high numerical aperture, this is the type of objective you will get. They are often white like that, or maybe always white instead of being a metal barrel. So these are two examples, and you can see here an objective like the 20x objective with really high numerical aperture and 1.8 millimeter working distance. So this is a very long working distance, and also a Nikon one that is 2 millimeters, so really long working distance. One more thing that we have to consider when we choose the objective is the contrasting method that we want to use for transmitted light. So we have said that transmitted light or bright field, which is what is used mostly in our field of microscopy, this method can be contrasted. So it's a non-invasive method, but it has a low contrast. To increase the contrast, we can use optical elements to increase the contrast, like for differential interference contrast or phase contrast. So these are the two images acquired in transmitted light with these two contrasting techniques. And you can see on the objective that here it is written pH3, and that means this is a phase objective. And you can see in here it's written DIC, and that means it's an objective for DIC. What does that mean? Different things for these two objectives. If we have a phase objective, we have a ring inside the objective. Unfortunately, we cannot remove the ring, and it distorts the point spread function for fluorescence. So try not to use a phase objective if you use fluorescence. Phase objectives are for transmitted light mostly. If you use like fluorescence with very big object, it's okay to use a phase objective, but if you are trying to see small objects, your point spread function is distorted. So the ring blocks the light. For DIC objectives, there is no element inside the objective, so that's very good, but we have elements elsewhere in the microscope that we need to actually have the DIC effect. So we have a DIC prism somewhere in the objective, and that also distorts the point spread function. So, but the good thing is that it can be removed. So if we have a DIC objective, it's okay to take images of very tiny fluorescent object with it, as long as we have removed the DIC prism. So, and again, it's the same thing. This is the type of distortions that you would expect for the point spread function. I think this is the last one, the aberration corrections. So inside the lens, so the lenses are, they are known aberrations that come with the design of objectives, and objective manufacturers correct for them. And you can see this written on the objectives as well. One of them is the flatness of the field. What is that? It means that the corner and the center of the image are not focused at the same place. Okay? So this is the aberration called field flatness aberration. The objectives that are corrected for this are called plan. Okay, so you will see plan written on the objective. Another aberration is chromatic aberration, and we have already seen this, an example of that. So you remember dispersion is one type of refraction, and that splits the color in a rainbow. The same thing exactly happens in an objective, and therefore the colors, the different channels, end up being not focused at the same plane, the same Z plane. These objectives are corrected. The objectives that are corrected are apochromat objectives. So this is also written on the objective or somewhere on the website maybe, but very often it's written on the objective. So the highest correction is plan apochromat, and you will see this written on the objective. Another thing to consider is the coating, and you can see sometimes this type of thing. So you can see here we have an apo, so it's written apo, but it's apochromat, so plan apochromat. And then here we have lambda D. This is the type of coating of the front lens. So there are crystal layers on the front lens to prevent a reflection of the emitted light, for example. So it improves the transmission. These crystal layers are fragile, so it's very important that you are gentle when you clean the objectives. This is an immersion objective. When you're finished with your work, you're going to have to remove and clean the oil away. You do not scrub the objective, okay? So you're going to have to watch a little video to teach you how to clean the objective. It's part of the assignments here. So how do we choose an objective? If we have if we need a high resolution, so we are imaging like dots and edges for our scientific questions, we need a high numerical aperture, and clearly we need a matching pixel size. We will talk about this next week. So high numerical aperture objective. If we want to go deep into thick samples, we need a long working distance. And if we have a thick sample that has the refractive index of water, oil, or mix, for example, a gel with cells grown in it, then you have a water refractive index, then you will want to have a water objective. If you have a sample that is thick and is a very high refractive index, for example, a cleared sample, then you will want to match and use maybe an oil objective, etc. If we have very large areas to image, for example, a multi-well plate, we have several wells, even if it's not the whole multi-well plate, but if we have several wells, long distances, or a big tissue section simply, then it is best without with an objective without any immersion medium, so that you do not smear the immersion medium on your sample. If you look at intravital, if you do intravital imaging on animals with windows, then glycerol objectives are best because the tissues have the same refractive index as glycerol. And then for super resolution objectives, for some super resolution techniques like turf and storm, we need ultra high numerical aperture above the critical angle. So this is very special. And if we have a very dim sample, we have looked at the brightness. Then we would want to try and find an objective that has a high numerical aperture, but a low magnification, because the magnification plays against the brightness. So do not use an objective just because someone told you pick that one. Please design your experiment and pick the best one for your experiment. Always use the correct cover slip thickness, so just go for 1.5. And if you have a ring on your objective, you need to set it to the correct place. And please clean the objective carefully, no scrubbing, okay? No pushing and scrubbing, you're going to remove the crystal coating. So this is a little example of some cells in a gel that were grown in a gel, and we were looking at all these collagen fibers. So this is very fine fibers, and looking at how the cells pull. And you can see this is deep inside, 60 micron deep inside this collagen gel, and we were looking at 60x water. This is not something you could do with an oil objective. And this is the very nice video, how to clean an objective by Cotton, that you will have to watch as well. So now I'm going to stop sharing and have a look at what I'm doing. I'm really fine. So I would like to know if you have any thoughts or reflections about this lecture about objectives.